So unless you're working on a brand new project, you often come across some technical debt. Even starting using best practices for all new code, well, what about all the legacy code? Sometimes this problem can be extremely overwhelming. Well, fortunately, we have Chelsea Troy, who is a staff engineer from Mozilla, to tell us about a systematic approach to solving this very often encountered problem in software development. Thank you so much.
Of course. Thank you for having me. Can folks see me? How are we doing today, folks? All right. Well, let me go ahead and share my screen to show you my slides that I have prepared here. And what I'll do is put this in present view. Are folks able to see that? Fantastic. So my name is Chelsea Troy. I am a software engineer at Mozilla. I teach in the master's program in computer science at the University of Chicago, and I work with a few clients as well. So today I'm going to talk to you about technical debt. If you've got follow-up questions after this talk, or you want to hear more of what I have to say, you can find me flinging corn in the giant online food fight that is Twitter at Hey Chelsea Troy. Or if your tastes are more civilized, you can find me being very well spoken about tech on my blog, which is called chelseatroy.com. And those two things are there in the bottom right-hand corner of the slide. So that's where you can catch me after the talk and always. But we've got a lot to cover today, so I want to get right into it. Right, so what is technical debt? We all have an idea of what it means to us, and that's why we're all here today in this talk. It turns out people have surprisingly different ideas about what tech debt is, so I'm going to use more precise terms throughout this talk. But first, I want to address what tech debt is not. There are two misconceptions to cover. The first is the one that equates tech debt with bad code. This misconception has two failure modes. The first is that it allows engineers to get away with thinking that the cause of tech debt is bad coders. The prior coders on this project were bad coders, and they wrote bad code, and we're good coders. So if we rewrite it, this isn't going to happen to us. So, number one, it's not likely that the people who wrote the system were just bad coders. It's much more likely that they were capable programmers under constraints that we don't understand. When teams endeavor to rewrite without understanding why the system is the way it is, they face a high risk of wasting a bunch of time rewriting, only to run smack into those constraints they didn't know about and not ending up with a better system after all. The second misconception is that if we just write good enough code, then it won't have any technical debt. And when we finish the feature, we can wipe our hands and be done with it. And that's not the case. We pay rent on every single capability that our system carries. We have to keep it working, keep it updated, keep it aligned with business needs. Every piece of code and every test for that code and every piece of documentation about that code adds maintenance load to the system. Maintenance load is usually the term I use when I'm talking about the thing people typically think of as technical debt. It's measured in units of developer effort. For example, one full-time developer's worth of maintenance load effort means that the team spends the equivalent of one full-time dev's worth of effort maintaining the existing system with things like updating, upversioning, or investigating existing code, determining whether a given feature ever worked, adjusting deployment so that existing functionality will scale to these new scales that we're hitting. Now, the heuristic that I use to calculate maintenance load is not perfectly accurate, but it's about 80% accurate and very easy to remember and use. And it's this: maintenance load comprises any developer activity besides adding a feature or removing a feature. And technical debt is maintenance load that comes to us specifically through the process of context loss. Now, what is that? Context loss is missing information about how, whether, or why a piece of the code base existed or worked. It can come from something that wasn't documented and the team forgot how it works. Only one person ever knew, and that person left. The code is so complicated that even the original author isn't sure what's going on anymore. And a system's maintenance load can jump dramatically when it experiences a context loss event. A context loss event might be the primary or sole developer changes jobs. Another context loss event is when somebody does a giant refactor that invalidates a lot of the team's existing knowledge of how the system works. The truth is, you don't know how maintainable or tech-deady a system is until it has experienced at least one context loss event. Before that, the original creators can hang on to a lot of the context and think that the system is in a more maintainable spot than it is. So, how fast does this maintenance load accrue? I want to quote you some maintenance load growth rates that I've seen. Maintenance load tends to rise as code bases get older because they get bigger and they have more features to maintain. I call this one the yikes case, but it's actually not the worst I've seen because I teach students who are completely new to all of this and understandably not that good at achieving code maintainability. Sometimes I'll have a student who starts a project and is the only developer, and 6 weeks later, they themselves aren't really sure what's happening in it. So when I say the yikes case, I'm not talking about a whole bunch of quote unquote bad coders. The yikes case is what I see on teams of relatively capable software engineers who don't really write too many tests, don't really document too much, and mostly have to focus on deadlines for feature delivery, often handed down to them by the business. It's one dev per 18 months, namely, however many years old the code base is, divide that by 1.5, and that's how many full-time devs it would need to stay on top of just the maintenance tasks. 3-year-old code base, 2 full-time devs. 6-year-old code base, 4 full-time devs. Just on maintenance load, not on adding or removing features. Now, admittedly, the yikes case is more often what I see on code bases that at this point are 10 or 12 years old. And part of the reason for that is that software engineering practice has changed a lot in the past 10 or 12 years. Testing and test-driven development just were not as common 10 or 12 years ago. The tooling that we had was not as advanced. The IDEs were not helping us out as much. And programming practice was in a very different place. So part of it is also that some of the practices that help us keep maintenance load down just were not as common then. Lately, the more common case I see is about 1 dev per 24 months. This is a team that tries to do a fair amount of testing and documentation. A team doing that consistently might get to 10 years out and have a code base that requires about 5 full-time devs to keep the lights on. Now, I wouldn't be surprised if some of you are thinking that my estimates sound way too high. Chelsea, there's no way my maintenance load is that high. My whole dev team is smaller than that, and we get by just fine. Maybe you do for now, but that doesn't mean your maintenance load is under control or that you will be fine indefinitely. Let's talk about some signs that your maintenance load isn't under control. Number 1, if you're making agreements with product to take on technical debt to deliver a feature, you're not on top of your maintenance load. You're making a bet that you're going to get to it later. Number 2, there are features that don't work and the team has just accepted it. If this is happening, you're not on top of your maintenance load. You're just declaring bankruptcy on maintaining certain features. Number 3, there are repositories or features that the whole team avoids. I call these abandoned houses. They're places where nobody wants to do work because they don't understand the system and they're terrified they'll break something. If you've got these, not on top of the maintenance load. Instead, the team is declaring bankruptcy on holding context for the whole system. So if any of these things are happening, we're headed towards continued accrual of maintenance load on the project. So we've talked about what maintenance load is and how fast it can rise. We know that older code bases tend to have more of it because there's more features to support there. But what differentiates the yikes case from the average case? And what might our team need to do to be an even better case than that, with an even slower maintenance load accrual rate? Here, I want to introduce a critical concept called code stewardship. Code stewardship comprises the skill set of reducing maintenance load. I want to note here, we cannot eliminate maintenance load. We can't do it because every feature requires maintenance. So in order to eliminate maintenance load on a system, you would have to eliminate the system. So if we've got a system, there's going to be some maintenance load, but we can try to reduce the maintenance load that we've got. Code stewardship skills include writing discoverable code so that new team members can treat the code itself as an artifact to understand the system and get up to speed. That helps make some of the context gathering self-service, which can be helpful to the team such that other people can continue to work on feature development while new members ramp up in part inside the code base itself. Code stewardship skills also include writing code with the malleability and rigidity in the right places. Now, this one has some nuance, so I want to spend a minute on it. Developers value code flexibility, and so they try to execute on the advice to make code more flexible. Everywhere, all the time. The thing is, when you stretch a stretchy material in one direction, it becomes less stretchy in the orthogonal direction. In the same way, developers who are optimizing for flexibility everywhere often end up with a code base that's truly flexible nowhere. They just sort of begrudgingly have to maintain pockets of rigidity all over the code base. Take, as an example, extracting a superclass. So we have two classes that are similar, so we have them inherit from a class that encapsulates their shared functionality. Dry things up a little, right? Except that when we do that, we're making a bet that these two classes' shared behavior won't change in a way that causes them to diverge. Because if it does, we now have to either go uncoalesce the logic into two separate new behaviors, which, by the way, is harder and more time consuming and more error prone than coalescing the identical logic later on. Sometimes developers refuse to admit defeat on this kind of thing and instead go do things like add conditionals to the superclass or add no ops to the subclasses, where we override methods in the superclass and make them not do anything in the subclasses. We made a bet that these two classes converge without considering the fact that if we are wrong and the classes diverge, we're going to have more work to do. So rather than blithely following edicts to make things flexible or dry things up, my recommendation is to ask questions about how and where the code base is most likely to change in the future, and strategically place the flexibility at those points, even if it is at the expense of other parts of the system. So for example, if I leave those two classes as separate classes and I don't extract a superclass, then if I have to make them have two separate behaviors in the future, that is easier for me to do. The code is more flexible in that direction compared to if that behavior had been coalesced into a superclass. Conversely, if I want to change both of those classes' behavior in the same way, I have to change it in two places. So it's marginally harder, I guess. It's marginally more work than if that same behavior existed in the superclass. And I've got to make a bet on how often I'm going to be doing the first versus the second. If I'm doing the first more often, these might need to stay separate classes. If I'm going to be doing the second more often, maybe extracting a superclass makes sense. And it can be difficult to tell when a system is new, how it's going to be changing in the future. For this specific example, I tend to try to get to 3 examples of a thing before I extract a superclass, because at 3 examples, the likelihood that these 3 concepts are in fact identical crosses a threshold where maybe it's worth it to me to extract the superclass and place that bet that these 3 things are the same. At 2 examples, I don't have enough evidence yet, but that's that specific case. The general case is look at how things are going to change in the future and allow that to inform your design, rather than using these sort of absolutist tenets of software engineering. So next is documenting code with detail in the right places. This is our 3rd example of a code stewardship skill. And this is another one where my take differs a little from the conventional wisdom. So, y'all, no documentation is bad. The urge to document is great. I'll just assume we're all in agreement there. But a 4,000 word README is not an especially effective method of documenting. So first of all, we're developers. Let's be honest with ourselves. Very few developers are capable of writing a 4,000 word long thing that anybody actually wants to read. It's just not a skill that we incentivize or develop as software engineers to make a 4,000 word piece of documentation engaging. So people are not going to want to read it. Second of all, in a document that long, a prospective maintainer or team member is going to have a hard time finding what they're looking for relative to if they knew the information they needed existed in some shorter document. I refer to this as the resume principle. So if you work in government, ignore the next 30 seconds of what I'm going to say, because you're required to have those super long resumes. But when I'm submitting a resume for a job application, I try to keep it under a page. And it's not because recruiters only spend 15 seconds on resumes or whatever. It's because I want to limit the things I am giving the interviewer the option of asking me about to the things I want to talk about. If I put every single thing I've ever done on my resume, then I give them the opportunity to flip back a few pages and ask me about a project whose design I came up with 8 years ago and it embarrasses me today. I don't want to talk about that. I want to only give them the opportunity to talk about the things that I think are the most relevant and demonstrate my skills in the best light. Similarly, with documentation, I want any given location of documentation to include the things that are going to be the most relevant to developers at that point in their development journey, and not a bunch of other stuff that's going to make it hard for them to find the thing that is relevant to what they're trying to do. Because all that time they spend trawling through documentation to find what they need, maintenance load. The developer spends 40 hours doing that. That's 1 dev's worth of maintenance load in a week. So rather than throwing everything into a README or a wiki or a Confluence or a read the docs, I recommend considering at what point is somebody going to need this piece of information, and embedding the information at that point, separate from the other pieces of information, so it's easy to find. Now, we've got a lot to cover in this talk, so I can't stack up too many soapboxes here about the art of documentation. The fun size version is this. There are a lot of kinds of documentation. READMEs are just one, and they're useful in some contexts, but not all contexts. We've also got code comments, automated tests, thoughtful error messages for when somebody's using our API incorrectly, commit messages, which give us a temporally relevant way to talk about what we were doing at a given time. We've got automated API documentation like we might get from Swagger. And we've got others as well. Each one works well for specific things we might want to document. At the end of the talk, I can share a blog post I wrote about that in the Zoom chat. But the point here is that a thoughtful approach to documentation can have an outsized impact on the maintenance load of your system. Another critical concept in code stewardship is writing tests that convey the code functionality and boundaries. Tests written at the wrong level of abstraction make code harder to change, but tests written at the appropriate level of abstraction should not only make code easier to change with confidence, They should also serve as little laboratories that allow us or teammates who are new to the code base to experiment with how it works. We can change the inputs to a test and run it and see what happens. We can change the format of the output and see how that looks. Finally, code stewardship includes the skill of transferring context to other members of the team. This is how we avoid those costly context loss events. It can include writing good pull request descriptions and making sure that reviewers could take over these changes if necessary. It can include effective pairing with others, or even some of the skills we've discussed before, like documentation and test design. It can include establishing buy-in with other members of the team before performing a giant refactor, because the bigger the refactor is, the greater the risk that it is itself a context loss event with implications for maintenance load of its own. Now, at this juncture, I want to issue a disclaimer on the accrual of maintenance load, because I've introduced this term code stewardship that makes it really easy to accidentally slide right back into this code is not maintainable because the previous coders were bad at code stewardship. No. There are systemic factors that contribute to the state of code stewardship in software engineering, and I'd like to acknowledge them here. So, first of all, developers tend to be rewarded and recognized exclusively for adding functionality. Developers get promotions, raises, bonuses, and kudos for cranking out features more than they get it for fixing lingering issues or keeping the trains running. And that's not their fault. That's systemic. And it's something we have to work on as an industry if we want the general state of code stewardship to improve. Second, product rarely holds features accountable for pulling their weight in constituent value relative to their maintenance load. Product is focused on adding features, moving forward. The way that the engineering team is paying rent on the features they assigned to be built in the past doesn't even necessarily occur to them, let alone is anyone going through and marking features for removal if their rent is more than their return. Third, tech education focuses on building things, much more than examining existing code or debugging methodically. Academic courses have students build things from scratch, and most tutorials are something like how to build X in Y. But most professional development work happens on existing code bases and requires learning and then keeping up those code bases. We don't teach those skills very well. Finally, high company-to-company churn and a fast-paced industry mean that few people have to maintain their own creations. The median time to stay at a job in tech is 2.2 years. And that's a high estimate from the perspective of context loss events, and here's why. That doesn't count developers who stay nominally at the same company, but change teams, which is very, very common, particularly at large tech companies. So the median time to stay on a team in tech is lower than 2.2 years. Because of this, relatively few people find themselves tasked with working on code they wrote 10 years ago, which renders a lot of maintainability concerns invisible to them. Okay. We've talked about how we might slow down maintenance load accrual, but we still have to figure out how to reduce the amount of tech debt we have right now. There's going to be two steps to this. The first is to figure out where the maintenance load is coming from. This step usually gets skipped in maintenance load reduction efforts. Instead, a manager usually succeeds in buying a team some time and then tells the team to take 3 weeks to pay back technical debt. What exactly they're supposed to do within this time remains unspecified, and often developers get to choose their own adventure here. The result is often that 3 weeks happen, the team rejoices, nary a feature is done, And then the period ends, and 2 weeks afterward, the team is over their heads in maintenance load again. What happened? Look, more often than not, the original causes of maintenance load did not get addressed in the payback weeks. Instead, a large portion of this unspecified 3 weeks usually went to code renovations. I use the term renovation in contrast to something like repair. When you regrade your basement, repair windows, or fix the roof of your house, the house gets better functionality. When you remodel the kitchen, maybe you like how it looks better, but all the appliances, the actual functions, remain the same. Code renovations are changes that developers make to working, maintainable code because that code doesn't match their personal architectural preferences. Pet refactors often fall under this category. These changes, they don't reduce maintenance load. And actually, they often erase context the team already shares about how the code works. And when the team loses that context, it drives maintenance load up. So, as we've discussed, a sufficiently large refactor counts as a context loss event. So, if there isn't a really good reason to do it, it often adds maintenance load rather than reducing it. And even if there is a really good reason to do it, if the programmer fails to establish buy-in or communicate the new pattern to the team, the context loss that the team suffers as a result of their choices might still outweigh the benefits of the change. So, how do we avoid these in our effort to reduce maintenance load? I recommend collecting empirical evidence on what developers end up having to work on besides adding and removing features. Some places to collect empirical evidence might be your retro notes. If you do a weekly retrospective, the notes from that can provide an avenue for developer complaints about the code base. And there you'll find some valuable information over time about what is consistently and repeatedly causing problems. You can also ask, when a time estimate goes over, what the holdup was and document those somewhere. Now, it's very important to do this blamelessly or developers won't talk about it. But when a time estimate goes over, what that might say is that there was some context missing here about how long this was going to take, and something within the process of making that change might have ended up being more complicated than developers expected. That might be a good priority for maintenance load reduction. So once you've got data like this, you can identify repeat offenders in the code base and then prioritize those when it comes time to pay back technical debt. That'll give you specific tasks that you can take on during that period rather than creating a 3-week choose your own adventure period. Other places to look would be signs of feature bloat or abandoned houses in the code base. So these are features that are no longer pulling their weight in terms of maintenance load rent. These are features that are not providing the requisite customer or stakeholder or constituent value relative to how long developers are spending keeping those features up and running. Abandoned houses are another, big portions of the code base or even whole repositories that nobody currently on the team feels equipped to work in. Once you've addressed all of these, you can look for places where the code flexibility doesn't match the rate of change. Maybe this is a code base where there's something really rigid, something that's really a pain to change, and people have had to change it a lot lately. It might be time to re-architect in that part of the code base. So once we know where the maintenance load is coming from, we can act on those priorities. What I'm about to describe is a rough priority order of changes based on average return on time investment or effort investment in units of reduction in maintenance load. They're not hard and fast rules, and your team might find exceptions to them. But this is a starting point for you and your team on getting the maintenance load down as quickly as possible. First, I'd prioritize removing any features that are not important enough for the product vision to justify their ongoing maintenance cost. The reason that I don't include feature removal in the maintenance load calculation is to deliberately incentivize it because of what a massive outsized impact it has on keeping maintenance load down. If we released an experimental feature that didn't end up working out for constituents, if it includes trappings that work poorly but constituents haven't noticed, if we built an email client and our product is not itself an email client, seriously, why is every app like, you know what else we need to be? An email client. You don't need to be an email client unless you're an email client. Rip it out. Leave your team time and bandwidth to solve the important problems it is singularly trying to solve. After removing features that aren't pulling their weight, I recommend addressing the issues documented in your retros and reappearing in your blown up time estimates. This is where that data we collected earlier comes in handy. This can tell you what will improve your tech team's velocity and happiness the most. Next, I recommend addressing abandoned houses at the point where a change is ended. I want to think pragmatically here. If you have a lot of abandoned houses, it's doubtful that devs can or want to address them all at once. But instead, you can encourage and incentivize developers to focus on the parts of these abandoned houses where they need to make changes right now. An analogy I've heard is to ask people to light torches in the tunnels they walk in and better understand the parts of the system that they're touching, rather than focusing on illuminating the whole cave all at once. I refer to the skill of figuring out how and why a code base works the way it does as forensic software analysis. Once devs have done this, they can again be encouraged and incentivized to document what they have learned to avoid the context getting lost again. After that one, my next priority is looking for places where the code flexibility doesn't match the rate of change, and consider re-architecting there. It's not unusual for devs to receive their blanket 3 weeks to pay down technical debt and start with number 4 in the list here. I think it goes after the other 3 priorities. But taking the opportunity to rethink the system after it's built, and most importantly, after it has been used and maintained long enough to generate information about how it's changing, it can be helpful to step back and reconsider choices made when some of that information was not available. I also want to mention here that for a large change in the architecture, there should be a period beforehand of establishing buy-in with the team and communicating about how it's going to change, to attempt to minimize the impact of the context loss event that the large refactor is bound to be. Finally, I recommend equipping engineers to suggest streamlining options. We often think of complexity and functionality as mutually exclusive. We have to give up one to get the other. That's often most true at the very low implementation level. But it might be possible to pop up a level and simplify code while expanding functionality. This idea is a little bit tough to communicate in the abstract, so I like to share 2 specific examples, a physical one and then a software one. The physical one is about launch pads. So down at Kennedy Space Center in Titusville, Florida, there are a series of launch pads that were used to launch the shuttles into space and are now responsible for launching things like SpaceX rockets and the Artemis missions. A launch pad in real life doesn't look the way that it looks in cartoons. It's not just a concrete slab that a rocket takes off from. There's a giant trench that the rocket is placed on top of. And then there's a tower next to the rocket that helps hold it up, and engineers use it to go up and down to perform maintenance on the craft. Astronauts generally go all the way to the top in order to get into a crewed spacecraft. Now, I suspect I don't have to tell you this, but when a rocket takes off, it generates a truly absurd amount of force. It's difficult to overstate the amount of force. We dumped 33,000 gallons of water down into the trench, so sound waves alone don't cause physical damage. We have to put burner posts in front of telephone poles anywhere around the launch pad so that the launch doesn't damage the telephone poles. Now, the tower has an elevator on it to help folks get up and down, like the engineers or the astronauts. The original towers at Kennedy Space Center had the elevators facing where the rocket launched from. So in order to prevent the elevator doors from getting damaged, heavy metal doors had to be installed on the outside of the elevator doors to protect them, much in the way we protect the telephone poles. And after each launch, engineers had to go up the tower floor by floor and pass a chain through the handles of the heavy metal doors and put a foot up against the frame of the elevator doors and yank them back into place, because the force of the launch would push in all of those protection doors. Later, launch pad engineers rethought the design of the pads. And now, when a new launch pad is built and when a new tower is built, they put the elevator doors on the opposite side of the tower so that the tower is in between the elevator doors and the rocket. Then the building itself absorbs the force. There's no more need for those heavy metal doors. There's no more need for the engineers to go up floor by floor and pop them back into place after every launch. You can think of those heavy doors as guard clauses. You can think of those engineers going up floor by floor as conditionals. Because of the system's redesign, those extra exceptional things became unnecessary. The functionality of the launch pad got expanded, the maintenance load reduced at the same time. Those types of redesigns can be useful in a software context as well. I like to provide an example having to do with a mobile app that I worked on at one point. Now, the idea of this mobile app is to allow volunteers to help with scientific research, like image classification of images that were taken by one of the rovers on the surface of Mars. Say we're looking for signs of water on the surface, and we've got 4 million images to go through. The 4 researchers on the project are not going to be able to do that in any kind of length of time, but what they can do is train volunteers how to do it, and the volunteers will go through on this application. One of the features of this application is that it allows volunteers to draw rectangles around things on the images. So for example, if they think that they see a sign of water having existed on Mars, they can draw a rectangle around that part of the image. Now, there are 2 modes on this app: insert rectangles mode and delete rectangles mode. During insertion, they can create and move rectangles, and in the deletion mode, they can delete rectangles. Once they switch it into deletion mode, the rectangles, which before were just green rectangles with no accoutrement on them, each one now receives an X button in one of the corners. It's a small green X with a transparent background, and it appears by default in the upper right-hand corner, unless the upper right-hand corner of the rectangle matches up with the upper right-hand corner of the image, in which case it moves to the lower left-hand corner, unless both of those corners are somehow obscured or behind the image or at the edges of the image, in which case the X goes into one of the other corners. Now, The reason that I was working on this code was that it had a problem wherein it worked fine on iOS, but it didn't work fine on Android. And it turns out that the reason was that the way the location of that X was being calculated, we created a number that matched up with the point system that iOS uses for placing locations of things, but it didn't match up with the way that Android does screen location placement. So in order to fix it as is and make it work just exactly the same as it already did on Android and iOS, I was going to have to go through and add a condition to each of those different locations of the X for iOS and Android, effectively adding a whole new layer of conditionals in there. Now, there were some other issues with that approach. For example, most of our tester images were plain black squares. And you can see a green X on a transparent background extremely well on a plain black square. But you can't see it particularly well if the image is of, say, grassland. If, say, we're asking volunteers to look at images from wildlife cameras and identify animals in those images. So a redesign was in order anyway. And I had the ability to go and talk to our designer about what that might look like. What we ended up choosing was that in insertion mode, the rectangles would be green, bright green. And then when somebody switched into deletion mode, there would be no X button. Instead, the entire rectangle border would go from being bright green to dark red, and volunteers could tap anywhere on the border of the rectangle in order to delete it. No more hunting for the button in a different corner every time. No more having to display a button in a different corner every time. No more reduced visibility button. No more conditionals for Android and iOS. Rather than having to add a new layer of conditionals, I got to remove a layer of conditionals such that we were no longer placing that X button in different corners dependent on different situations. The code got simpler, the functionality got expanded, and volunteers had an easier time using the app. But that was only possible because I had the ability to go to the designer and have that conversation. It would not have been possible if I had to take the commands passed down from another part of the organization and execute that design such that it worked for Android and iOS. So when you empower engineers in your organization to suggest those streamlining options, you can often end up with better software and a better product. But the reason that this one is number 5 is that it takes a relatively large investment on the part of the team, because sometimes it can mean changing team norms about the way that decisions are made. Nevertheless, I think it can be useful. And once a team has used priorities 1 through 4 to dig themselves out of some technical debt, I think number 5 can be a useful approach for preventing further technical debt and potentially rethinking some of the perennial sources of maintenance load in the code base as it is. So those priorities provide a starting point. As you start these conversations with your team, you'll run into the hard thing about hard things. They're all different. Every system will have its own idiosyncrasies for you to navigate, and every team will have its own social idiosyncrasies in addition to the technical ones to navigate as well. But my hope is that what you've learned in this talk will help with both of those, because it will give you tools to see and address some of the maintenance load you have right now, and the language will provide handles on slippery concepts to help you get your whole team on the same page. And I hope you found something to take away from this talk, and I'd be thrilled to hear from you about your adventures in maintenance load reduction on Twitter or via email. I'm chelsea@chelseatroy.com. So.
All right.
I'll yield my time, I guess.
Okay, so Q&A is going to happen in room A. Let's see.
Room A. I will stop sharing. Now we'll go over to room A.
Wow, there's questions popping up. All right, I'm just going to repeat the question for the sake of video. Teams sometimes take shortcuts in the name of business priorities, not only choosing to cure technical debt with promise to pay it back later, which rarely happens. How can we hold these teams accountable to clean up the messes they made?
Well, that's an interesting question, because a lot of times this speaks a little bit to the point about the systemic causes of some of this. Like I said before, I think that a lot of times we run into situations like this in a code base. It's not that the developers were incapable, it's that they were under constraints. And a very real constraint that a lot of teams face is that the business is asking them to execute something on a deadline, and they have to hit that deadline. And the business maybe promises them that they can go clean it up later. But then once the deadline is hit, suddenly the business has a new deadline and they need the developers to hit that too. So this can be a hard one. And this is part of the cultural change that needs to happen in order for maintenance load to get under control in the vast majority of cases where it isn't. I find it most helpful to start with product rather than the business, because I find that the product team generally has the ear of business on what needs to happen. And in addition, product managers have more software experience, I'd say, on average, than business folks who are asking for these priorities. So I find it helpful to start conversations with the product team around whether we can hold the features accountable for pulling their weight in terms of constituent value relative to their maintenance load, rather than holding the developers accountable for cleaning up the messes that they make. In general, developers don't want to work in a messy code base. It's hard. Velocity is slow. It's difficult to keep context on everything. It can be very frustrating. And given the option, they don't want to work in that situation. And they often have the skills to get themselves out of that situation, but they just don't have the time to get themselves out of that situation. And by framing for the product team the maintenance load of the existing system in terms of how many developers have to keep things running right now, and therefore how many developers they lose that they cannot count on for their feature development efforts, that can help incentivize the product team to help find those features that are costing the most in terms of maintenance load, and decide whether those features are worth their cost in maintenance load, because product will find themselves motivated to reduce the degree to which velocity is impaired by the features that are already there. And once that can happen, and once the features that aren't working very well, aren't very useful, and are costing a lot in terms of maintenance load are removed from the system, it ends up being a more streamlined system, a smaller system. Maintenance load on smaller systems tends to be lower. And then once that's in place, the team has more bandwidth to continue moving forward on products priorities. So I'd say that there's more than enough accountability to go around, but we can spread it more evenly in order to end up with a better result, rather than expecting developers to be able to clean up those messes on their own.
Would it be helpful to also say that some of these features are actually costing them, like support tickets and stuff like that? Because once things, once you have a thing to twist, some people might want to do it, and if it doesn't work properly because nobody maintained it, then they create a support ticket where if they didn't have that thing to begin with, then
absolutely
no feature, no problem.
Some of the most convincing conversations that I've had with product in this regard have been discussing maintenance load in terms of full-time developer effort and saying, look, we've got a maintenance load here of 3 full-time developer effort, and we've got a team of 4 developers. What that effectively means is that the reason that features aren't getting cranked out the way that you would like them to is that although it's a team of 4, you really only have 1 developer at a time able to work on those things. And at that point, product starts to see like, well, like these are problem solvers, they want to find solutions. And once the problem is framed for them like that, they'll start solving for how do we get to where more developers can focus on the features that we need.
Okay, Sujan has a question. It says, I think one of the biggest challenges with making tech debt a part of the process is humans do not like hearing negative news. Pumping the brakes, taking detours, making U-turn are all valid options, but they're viewed negatively. Teams and leadership that encourage discussion of risks and constructive criticism without repercussion, i.e. psychological safety, tend to outperform teams that don't. In your experience, how do you encourage teams and leadership to do this? How do you empower teams to be comfortable with this?
Well, I think the most valuable tool that I have found in that regard recently has been having a unit with which to express these things to the business. So in general, the way that managers have traditionally gone about attempting to advocate for these things is by going to the business and talking about the plight of the engineers and attempting to buy 3 weeks where they don't have to do any feature work. And then the business doesn't want to do that, but they begrudgingly accept. And then the team blows it on all their favorite renovations. And then we don't end up really in a better situation. I have found that the language of maintenance load helps to align incentives a little bit more in that regard, because I can say to a business, all right, we've got 5 developers. Our survival rate is a maintenance load of 3 developers. Our actually improving things rate is probably more like 6 developers. And then once they have that information, I can say, look, listen, the choice is yours. We can continue to survive on 3 developers worth of maintenance load, which leaves you with 1 developer's worth of features, or we can continue to try to employ people on features, but that survival rate is kind of what it is. So for example, I was reading an article recently about the amount of rest that people need to take, and it said that people need to be resting for about 42% of their time. And this article, it made a very interesting point, and it's something that I remember very clearly from it. It said, it's not that you should take 42% of your time to rest. It's that if you do not take the 42% will take you. You will end up unable to focus. You will end up forced to rest. Your body will force the issue. And the same is true of the survival maintenance load rate. There is a point at which, if the team is not taking the time to address the maintenance load will take the team. There are things that absolutely have to be done that are now blocking the feature work. And it will be impossible for the team to crank out those features without addressing those pieces of the maintenance load. And that's the survival rate maintenance load that I mentioned before. By providing those numbers to the business, I can give them the agency to make decisions, but I find that they tend to be more supportive of the decision to allow developers to address maintenance load because they've been provided with the information and have been permitted to make the choice to prioritize that, sort of, more than having been told by the dev team, like, we have to stop and deal with all of this stuff. Now it's more clear to them the units of productivity, if you will, that they are losing to this situation. And once that cost is made visible to them, they tend to be more motivated to reduce that cost than just being told that there's this black box development team and you need to let it output nothing for 3 weeks or else it's going to stop working. That's harder to understand, and I think harder to get behind for folks who aren't in development themselves.
Especially when the 3 weeks may not result.
Mm-hmm.
Yeah, no, the measurement is key. Though people love numbers and they love being able to lower or game the metrics, as we heard in the Jessica's talk before. Okay, yeah. One more question. Is NFR debt a thing? Meaning a system that is used to meet expectations for all the entities, entities, undergoes user and traffic growth and now no longer meets reliability, availability, scalability, etc. So the team needs to include NFR improvements along with feature development in a similar way, working off technical debt. Seems like a parallel challenge for the organization.
What does NFR stand for?
That is a good question. NFR, non-functional requirements. Ooh, Daniel, always with the translations.
Okie dokie. You know, this is an interesting question because this gets into what counts as functionality, and effectively what counts as a feature. And I think that we have a tendency in tech to prioritize functionality over other things. And that can make it difficult to talk about what is a feature because things like non-functional requirements don't make the grade in folks' minds as features. I find it easier to advocate for the time that needs to be spent on those things by describing them as a type of feature in and of themselves. Functionality is one category of feature. Another category of feature is scalability. Another category of feature is robustness. Is things going to break if somebody uses them wrong by accident? Another category of feature is security, right? This is one that teams really don't like to spend any time on, because if the security is good, the result is nobody ever hears about it. And that can be a really difficult thing to advocate for at the business level. And then we end up with all kinds of things like, oh, Equifax never bothered updating struts, and whoopsie, 140 million people's social security numbers are now all over the internet. So these are things with a very outsized impact that it can be tough to advocate for if we don't consider them on the same level as functionality features. And so making that distinction, I think, is helpful in advocating for what we might consider to be non-functional requirements to get onto the board as priorities. That we've got a variety of different types of feature. Functionality is the most visible one. There are also all of these other features. And if we don't address those features, then we face all of these relatively catastrophic risks of constituents leaving us because our system went down, constituents leaving us because their information isn't secure, or even opening ourselves potentially to litigation if we lose something that we said we would protect. And if we are able to articulate those risks in a clear and quantifiable way, we'll have a lot more success talking to the business about them, because usually it's not that the business doesn't care about them, it's that they don't inherently see it unless we can communicate it properly. And once we're communicating it properly, the business's loss aversion takes over. Nobody wants to lose something that they already have. And they have a very strong incentive to allow us to prioritize those features as well.
For sure. No one cares about security until they have to deposit $2 million into a Bitcoin wallet.
That's right.
In order to unlock their stuff.
Exactly.
All right. Well, thank you so much, Chelsea.
Absolutely. My pleasure. Thank you for having me.